excited to be talking to Peter today. He's got a lot to say about artificial intelligence and all sorts of other things. Incredibly interesting thinker. What are your thoughts?
Yeah, I know that he's very focused on the potential in with cancer and medicine, and we don't hear a lot about that. We think of all the other ways that AI is coming into our lives. So yeah, I'm very excited to talk with him. All right, let's get on there. Today with us we have Dr. Peter Lee. Should we say that you are Corporate Vice President Research and Incubations at Microsoft, and you lead research across 8 laboratories around the world?
Peter, when you think about artificial intelligence or technology in general, does technology have a purpose beyond, we sort of all get caught in the idea of hearing about it all the time, but is there a purpose to technology?
Yeah, I think there are a couple of things. One, of course, with global crises like COVID-19, climate calamities, things like wildfires and so on. One thing that we're finding out is that ideas in technology, research, science are becoming more urgent and urgently needed than ever. And so there's just the very practical thing, knowledge is power, that scientific knowledge gives us tools to be able to help cope with things. But I think there's something even more fundamental, when you're doing research. There was a famous essay a long time ago by Flexner entitled "The Usefulness of Useless Knowledge," which really sort of set out the reason to set up the Institute for Advanced Study at Princeton. And, it just made the fundamental case that just the discovery of new knowledge, of new scientific knowledge, inevitably, I guess the way I would put it, brings you luck. You find yourself suddenly in a position where, for no intended purpose, some new knowledge that was kind of laid out maybe a decade or 2 decades earlier suddenly becomes absolutely critical knowledge. And that's just something that happens over and over again. And so it's hard to know if that's a purpose exactly, but it certainly has ended up being really meaningful to the human condition.
Kip Thorne won the Nobel Prize for something that he thought about, 50 years ago about waves, being able to see gravity waves. You're involved with all these labs. People don't. It's very hard to get people to fund basic science. Do you let people go just thinking about, like, hey, you're onto something, just keep going, or how do you do that within a structured environment? I mean, because you worked at DARPA too, where I imagine that's all about basic science. You have a somewhat different responsibility.
Well, it's something that the idea that basic science is valuable, I think is exceptionally fragile. And it's something that, in a way, you have to actively think about and keep alive. I think every scientist goes through this in life. In fact, for me, I grew up in a household. I have my father is retired, of course, but he was a physics professor. My mother, who passed away, was a chemistry professor. So if you imagine growing up in an Asian household with 2 physical science professors, it was pretty hardcore. And I joke that it was a huge disappointment when I went to college to study computer science because I couldn't possibly be as legitimate as the physical sciences. And while that's a joke, it also kind of captures sometimes the things that you have to go through when you're just in a pure intellectual pursuit. It's analogous to what artists have to go through when they're pursuing their craft. And I remember as an assistant professor, we had a change in department head, and I was meeting my department head, and I explained to him, what kind of research I do, and he sort of frowned and didn't understand why I was doing all this theoretical fundamental science, and I blurted out, just trying to defend myself, well, it's just so beautiful. To which he said, well, if you feel that way, maybe you should be over in the fine arts school instead of here in computer science. And so this idea that, you know, of keeping the flame alive, of understanding and constantly explicating and proving out the value of science is just a deep part of the culture of what we do. And Microsoft Research within Microsoft does that for the company, and by extension, you know, participates in that broader discussion.
You know, physics at the highest level, you know, there's universal principles. Then you mentioned computer science. You're always trying to understand maybe statistics, and then you talk about fine art. Is there a similarity between these things? Because when you say it's beautiful, all those things are beautiful in different ways, no?
It's a good question. There are some things that are just stunningly beautiful. You know, when I actually started off as a math student, not computer science. I didn't get into computer science until I finished my undergraduate degree, and then went to grad school. And what convinced me to switch to computer science is this idea of something called the Curry-Howard isomorphism. And so basically it's this idea that there is a correlation between mathematical proofs that you would write in certain types of mathematical logics and programs. And this correlation sort of showed that there are certain types of programs that you can write that can't be captured in any existing mathematics. And so it's super esoteric, but you know, you sort of confront this incredible crystalline beauty of some deeply fundamental thing. And then you have the excitement that on top of that, these things can be real machines that you put in people's pockets that do pretty cool things. And so that combination, I think, is the idea that something so esoteric can be so kind of widely available and practical to people is, I just find incredibly beautiful. So, you know, I don't know very much about art, although my wife is a retired painter. But sometimes art can feel inaccessible. But when you have those magical moments where an artist is able to do something really avant-garde, but that still connects to people, you know, in a way, maybe there's an analogy to a lot of computer science.
Peter, can I ask you a question for the audience coming in? You know, you have a shorthand with Jesse a little bit about what you do, but I think for people listening, you know, within the labs, what are we trying to do? And, you know, we're working with artificial intelligence, and people don't know, I don't think have that context yet. And one thing I was going to say, where you're talking about science, so science is agnostic, but does AI have bias? And how do we think about that? And kind of just writ large a little bit more about the work that you're doing and where we're going with it.
Sure. So I think of my job as trying to understand what is inevitably true about the world in the future. So it's 2020 now, so it's easy to think about 2030. So what is definitely going to be true through some combination of economic, social, technological forces? And based on what I think is inevitably true about that future world, what do we have to understand and study today? What do we have to develop today in order to be ready or to be able to contribute or take advantage for Microsoft's business in that future world? So to take one example just out of healthcare, by 2030, we have supreme confidence today in the scientific community that cancer will be largely solved over the next 10 years. The progress has been so rapid, and it may not be cured exactly, but it will at least be a manageable disease, much like we manage diabetes. But now, if you look across North America, across Asia, across Europe, we see this silver tsunami of this aging demographic that is likely to lead to a huge rise in age-related neurological disease. In fact, today, let's just take the US. The National Institutes of Health spend 60% of their research budget on cancer. That is very unlikely to be true in the year 2030. just because of the progress in cancer and this silver tsunami. So now, as we think about the research that we do in biotech, biopharma partnerships, in computer science to support neuroscience, this has implications. We can try to work backwards and understand, well, then what are the kinds of research efforts and areas that we should be investing in today? And so that idea of just looking beyond the headlights of where our current businesses are looking, trying to understand those major mega trends for the future, and then helping you stay ahead of that. That's basically the mission of Microsoft Research. And
You know,
yeah, go ahead.
please continue. You know, we always hear a lot about big data. You know, and we've seen some forays into trying to understand it better. You know, the promise of Watson, I don't think it ever achieved its promise, but the promise would be that a physician could sit in a room, and there's so much research being done out there that we can't, you know, no human being individually could be up to date on where you might be. You know, what's the, when you look at statistics, you know, how much good medicine, how much better outcomes is buried in the statistics, but we don't know how to get it out yet.
Yeah, there's a good news, bad news thing going on there. So first of all, with respect to big data, it's hard to overstate the amazing things that are happening right now. And, you know, in an earlier discussion, I was, you know, saying, I don't know if either of you have learned a second language, speak a second language, or tried. My wife speaks French pretty well. And so I've tried to learn French, but it's pretty painful, even to my ear. I don't like to hear myself speak. But one of the things that happens when you learn a second language is this psychological process called transfer learning. You use your base native skill in English to learn that new language. It gives you a head start. And that idea of transfer learning is very deep. It's not just learning the new language, but actually learning how to ask questions, how to answer questions, how to tell a joke, all those things. And the other thing that happens is the transfer effect goes in both directions. When you try to learn French, your English gets better. And this idea of transfer learning is turning out to be present in the AI systems that we're training on big data. So today, for example, one of the most exciting developments is that we're able to build AI systems that ingest just unimaginable amounts of text data just from the internet and build models with hundreds of billions of parameters that are just learning the essential structure of how letters are put together into words, words put together into sentences, sentences put together into whole documents. And from that, then we can have very simple training that allows these AI systems to answer questions, to predict just based on one or two kind of prompts, what the whole rest of the document should be, you know, actually kind of auto-author these things. And when you start to apply these things in the medical domain, you get to practical outcomes. In one project we have at the Jackson Laboratory, which is an NCI cancer center, we're ingesting 2,000 cancer research papers every single day, building a knowledge graph that provides decision support for cancer treatments. During the COVID crisis, we've deployed at over 2,100 hospitals and clinics interactive conversational chatbots so that people can self-assess their symptoms. And this is now the chatbot on the CDC website, as well as other government websites around the world. There's a product powered by this kind of technology by Nuance that listens to doctor-patient conversations and automatically sets up the clinical encounter note so that, you know, the doctor doesn't have to spend all of his or her time at a computer in the exam room. And so all of these things are sort of possible just with this incredible advance of our ability to just ingest language and then easily transfer that base knowledge to all these other skills or tasks. But at the same time, it's very difficult in a way. So the kind of idea that you mentioned is is captured in this concept called real world data or real world evidence. And so the question is, are we able to just observe what happens to actual patients as they get treated in order to extract new medical knowledge? And in principle, based on all of our AI capabilities, that should all be possible. But in practice, it turns out to be much, much more difficult than one would expect. So during the COVID crisis, there was a lot of authorization of experimental treatments for COVID-19 for compassionate purposes. One of the largest was the compassionate application of transfusion of convalescent plasma. So if you had COVID-19 and you've survived, you have antibodies, so you can extract those antibodies in a person's plasma and then transfuse that into a sick COVID-19 patient. Now, the US authorized under an early access program that treatment, and over 80,000 people in the US were treated, anecdotally with very good results. And so the question is, well, based on all of that, shouldn't we be able to extract the knowledge on safety and efficacy of that treatment method? And while eventually that was accomplished, and the FDA did authorize that treatment for emergency use, it was exceptionally challenging from a computer science perspective. And the algorithmic challenges ended up being very difficult. The data challenges, our health system isn't set up to collect all the necessary data. And so we have still a gap between sort of the reality of that vision and what we know is possible. And it's in that gap that I think we still have a lot more work to do.
Do we not have the most sensitive analytics tools, or diagnostic tests? Is that one part of the problem in order to get the information, trying about this plasma issue? And then a second issue is you run into the, IRB issues about how you're going to show the efficacy and what it means, and the peer-reviewed issues, which are not computer scientist problems, they're people problems.
Well, to give you a little bit of a sense of some of the complexities, when patients are admitted to the hospital, and if they have COVID-19, one of the complexities is that after, say, about 72 hours, if the person is still sick and in the hospital, sick enough to be in the hospital with COVID-19, the vast majority of them have other problems, pneumonia, some other kind of blood disorder, some even with some kind of neurological symptoms. And so suddenly things get a little bit muddy because you don't know now what the effect is. In fact, normally in a randomized control trial, you'd want to control for those sorts of variations. People will be all different ages. There'll be different races. They'll have different comorbidities. Hypertensive patients seem to respond differently than others. And so when you start to try to extract the moral equivalent of a controlled study or trial, even from a large cohort of over 80,000 patients, that large cohort starts to get disqualified, and you get down to now a much smaller group than you would have expected. And then, data collection is a little bit sketchy, because in the electronic health record, early on, this is a novel disease. So there were no standard codes for COVID-19. So it's not like there's a structured data element in any electronic health record in the early part of the pandemic. And so suddenly you have an AI problem just to read the free text in these electronic health records to understand who are the COVID patients. And it goes on and on like this. And so, it's not a controlled environment. And so the data is difficult. One last thing to say is we use the term big data. And so in my world at Microsoft, big data means something like internet scale. And what is exciting is we now have the computing power and the capacity to actually absorb data at that scale and produce working AI models. When you're dealing with a disease, even one that's involved with a global pandemic like COVID-19, the numbers are small. In fact, there are only 7.5 billion people on the planet. 7.5 billion is not a very large number for a computer scientist. And so what we mean by big data is sometimes a little bit different.
Can I jump in and ask you a question? You said in the beginning of this conversation that possibly, in 20 years or 10 years, cancer would be more chronic, or we're going to get to a new place. So if you could just talk about, is it that you have the control groups? I mean, is it that you're actually studying tumors as opposed to this unsuspecting thing that hit us, the pandemic, where it was coming, it kind of probably wasn't in the predictive model in the same way. Somehow an AI was like, whoa, what is this? But for something as small and as targeted and as deadly as, tumors, what is the difference? How is that going to be possible? What would be the application of what's happening in the lab? I'd love to hear more about that.
Well, I guess for cancer, this has been a multi-decade journey. And the scientific advances, have just been adding up, and it's amazing the amount of effort and resource that societies around the world have put into cancer. I mean, think about it. About 2,000 new research abstracts and papers are posted in cancer every single day today. That's just a massive amount of human knowledge that's being applied to cancer. And it's adding up. We're going to be able to beat or control this thing. And that, of course, is based on a lot of fundamental knowledge that applies to other, to other diseases as well. Because, for example, with the rise of cellular therapies, we just understand a lot more about the mechanisms, the biological mechanisms in people. And, those things come into play, for example, if we're trying to find therapeutics for COVID-19 or for other diseases. When I think about neurological disease, it's in a way, it's sort of like where we were 2 decades ago with cancer. We don't really have the same level of biological understanding, the mechanisms of the brain that gives us that biological foundation for understanding how to treat or diagnose neurological disease. So, the guess is that we might need to establish that, and that maybe it would be a smart thing to start looking at that now. And then to connect that to Microsoft's business, that is all then happening at the same time that the fundamental infrastructure, information technology infrastructure for medical research and for healthcare delivery is becoming very data dependent. And, for reasons that Jesse had mentioned earlier, is seeking a way to aggregate many different sources of data together so that you can get a more holistic picture of people. And that has huge implications for any company that's investing in the cloud like Microsoft is. So putting those two things together just makes it a very important thing for us in Microsoft Research to spend a lot of time thinking about.
Why is Azure, the program Azure, important to bringing in all these different kinds of data at the current time? Maybe they don't speak to one another. Why Why is it important to put resources there?
Again, people don't know what Azure is. So what is it and then how is it? Just for the layman people.
Sure. So Azure is a cloud computing platform. It's what's called a public cloud. And you can think of it as an elastic computing platform. So you can get computing power and storage that can scale up and down at your command. Azure is also takes very seriously data privacy. And so even though we have many what are called tenants, many different people using Azure, each tenant on Azure has the illusion that they are the only people on the entire cloud. So it's as you are given the illusion and the actual data privacy that nobody else exists on this cloud. The fact that Azure has this kind of ability to scale at will to extremely large sizes, has a global access footprint, and has this data privacy, makes it, we think, ideal for healthcare applications. Because it would be a place where, say, a health system could aggregate all the genomic information that they have, all the medical images, all the electronic health records, all other sort of patient records, scheduling information can all be aggregated into one place. And if you achieve that, then you have the ability to be able to apply analytics that work over it all. Furthermore, other elements of the cloud, like Teams, or for telehealth, or health bots, all live on that same cloud. So they can all be integrated together. And so instead of having 80 different silos of data on 80 different systems in a hospital or health system, in fact, in some hospitals, even different departments have their own IT systems. You would have the ability to kind of bring all of these together into one place. One of the dreams here is that in doing that, this shift to the cloud, like Azure, which is also happening to the other major clouds at Google and at Amazon, at IBM, this is something that will happen once in human history. This is 20% of the US economy that is undergoing this shift in its fundamental computing infrastructure. And so one question we can ask is, as this shift takes place, are there specific interventions we can make right now to give us a chance to be in a better spot once this shift completes than we are today? The commissioner or the head of Medicare and Medicaid Services, Seema Verma, she tells this compelling story. She was on a vacation in Hawaii with their husband and 2 daughters. This was in the previous administration. And as soon as they get to their place in Hawaii, Seema gets called back to DC for an important meeting involving the president. So she's boarding an airplane to fly back. Her husband is playing on the beach with the 2 daughters, and then suddenly he falls unconscious on the beach. And so emergency medical technicians come. They're trying to figure out, like, what's wrong with this person? Does he have any other conditions that are relevant here? And of course, the 2 little girls have no idea. And so the inability to have any idea of how to access this person's health history, it was a matter of life or death. And so the hope is that by providing the ability to have data standards that are modern, just like the World Wide Web, but still manage privacy, align with all the kind of regulatory requirements, that if the cloud can provide that, then we can have a much better health system.
You talk about the end of cancer. If you go into an institution, they might say, well, you need immunotherapy, or you need proton therapy, or you need this, or you need that. And the doctors are making that decision based on imperfect knowledge. What do you think when we say personalized medicine, what does that really mean with all of this data that's floating around? Like, how are we going to shape that and get it into a doctor's hands at the point that they could actually make a decision that would lead to a better outcome? You know, what's the promise of all this?
Yeah, there are two things to say there that I think are really interesting. One is, you know, when you do go to a cancer center, you're right. The doctor is necessarily not going to have all the latest information. There's just too much of it coming in. And at many cancer centers, there is a board of people, a tumor board or molecular tumor board that, you know, might involve a dozen experts. And so if there's a proposed treatment, just based on the knowledge of your genetics, the genetics of your cancer, other factors, you know, they might have a better chance of having more knowledge to understand what treatment is right for you. But even that, you know, is sort of hopeless, just given the flood of information. And so here, this is where decision support tools that are able to ingest those thousands of new abstracts that get posted every day and synthesize them into a knowledge graph that powers a decision support tool becomes really important. And so the decision support tool that the Jackson Laboratory uses now, which is used by about 70,000 cancer specialists around the world, is in fact powered by just such an AI system. And that's in a project which is called Hanover here at Microsoft. But the other thing is, at a more deeply fundamental level, one of the things that has happened with our knowledge of the human genome is to be able to look at some of our immune system dynamics as a language problem. And so just to take one example, in a project that we have with adaptive biotechnologies here in Seattle, if you take a 1 ml blood sample, you end up capturing a sample of about 1 million of your T cells. And those T cells, each one of those T cells is genetically programmed to attack a specific antigen that causes disease. And so that genetic specificity is controlled by a specific protein, which is characterized by a small snippet of DNA. And that is speaking a language. And in fact, you know, that printout of those 1 million pieces of DNA from those 1 million T cells is saying something about the diseases, the cancers, the autoimmune disorders, or infectious diseases that your body is coping with right at this moment. And so with adaptive biotechnologies, they have proprietary sequencing technology that's able to quickly and relatively cheaply produce that printout. And so now the question is, can we translate what that printout is saying into the language of disease? And that turns out to be a machine learning problem that's not too unlike the machine learning problem of translating, say, English into French.
So is it like like taking a language of human beings and you know, we don't know exactly how they were created, and then is there a corollary between the language of genes?
Well, there was a breakthrough 5 or 6 years ago in biology to understand something called the TCR, T cell receptor repertoire, which really isolated or hypothesized that this specific protein on in the T cell receptor characterized completely the specificity of each T cell. It's looking more and more likely that that's correct, that's a true hypothesis. And so with that, then we do end up with a translation problem, which in terms of scale is very similar to the problem of translating between human languages. So roughly speaking, just in the size of the neural net that you would need to do a good job with that, it ends up being roughly in the same ballpark. And so adaptive biotechnologies has been using that machine learning technique then with our help to target specific disease diagnosis problems. Can we diagnose Lyme disease as an infectious disease? Can we diagnose ovarian cancer in stage 1 instead of waiting to stage 3? Can we diagnose autoimmune disorders like celiac disease?
So in in ovarian cancer, you have a pattern that if you look back through the data, you might find the genes that actually were, that we didn't recognize, but now we do recognize because we see them further develop later. In autoimmune, it's much harder because there's only 11 of 13 symptoms. So how do you find a pattern that you can predict? Is that a machine learning problem?
It ends up being machine learning because, roughly speaking, you are able, in essence, to understand from this sample of your T cell repertoire, what sets of antigens are active, just by looking at what of these T cells are likely to have been recently what's called clonally expanded. And then from that, so that ends up being very similar to a language translation problem. Then from that, you have a second step based on that result to pick out the topics, which you can view as, as those diseases.
So when you say AI, in that example, it requires a researcher to look at it and understand what it is and point it in the right direction. So is AI always coming back to the human being, and then the human being's making a decision and pushing back? And is there a, how do you keep that, going in the right direction?
Yeah. So it's, there used to be, I would say 3 years ago, if we had this conversation, there was a very simple answer to your question, which is yes. There is always a human in the loop, and we're always dependent on producing label training data, where the labels are coming from human intelligence, or the way I like to put it, the digital exhaust from human thought. But today, it's much less clear. There is now, for example, in these large pre-trained models for language, these systems are more self-supervised, meaning that, yes, we are building these models by ingesting extremely large amounts of human-generated text. But then what you can use those models for can be directed at problems for which there's been no human intervention, no human labeling. And this is an effect that's sometimes referred to as zero-shot learning, where you can apply these models to tasks for which there was no training. Specifically. And it's very tempting, although you have to be careful to make analogies to the way humans learn. Humans have, I remember my son's 23 years old now, but when he was a little child, it's pretty amazing. You teach a little child, you show a picture of a Tyrannosaurus Rex and you say, that's a dinosaur. And then based on that one-shot learning, you can show a picture of a velociraptor and the child instantly knows that's a dinosaur too. And furthermore, there's a zero-shot element of that because, the child implicitly has learned, all dinosaurs have legs. All dinosaurs have tails. Again, with no training data there. And what we're seeing is that in these emerging, extremely large self-supervised systems, that these one-shot and zero-shot effects, as well as transfer learning effects, are emerging out of these things. And, it's very, we don't fully grasp the full practical implications of this, but we're just observing more and more of these kinds of effects coming out.
I have a question, Peter. I mean, based on, it's all incredible what you're talking about, and there's also the ethics and the kind of the fairness and all of those things that I don't even want to get into today. Maybe you'll come back another day. But are you thinking now that, for example, we could ask the system, and do you think of it as a AI or whatever you're calling this system, to start to design trials for us as well? So, starting with from ground zero, can we ask to go in to ask a question? Can we ask the machine, the system, the learning system, to ask a question that might answer a problem we don't even know is there, or to design a trial? You're talking a lot about the brain moving forward. We know so little about the brain, so I'm assuming a lot of the work is going to be around Alzheimer's. And we spoke a little before Jesse got on, like trying to keep our memories going. But can we start doing that and will the system understand enough to start to create trials for us, if that makes sense?
Boy, there's so much in what you're saying. First of all, the issues of fairness, accountability, transparency, ethics. In fact, within Microsoft Research, this is codified in a research area in which we're very heavily invested, that we call FATE, for fairness, accountability, transparency, and ethics. Plus, as a corporation, we have a governance process on AI ethics called Ether. And, and so whenever any employee raises a question about, should we or should we not allow this form of facial recognition into a product, any employee is able to raise that question. There's a whole governance process that tries to adjudicate these things. I would say from the research perspective, really understanding these issues and even building tools to help mitigate risks, to understand risks, and to provide some foundation for this type of adjudication, which ends up being a human process. All of these things are really have become super important. And if there's one worry I have is traditionally those research explorations have lagged behind the frontier of what's getting deployed, by several months or maybe even several years. And so one reason why we're investing so much there now is we're trying to get that to catch up, because you really want to stay, at least a little bit ahead, if not pretty far ahead. And so that's sort of an ongoing battle right now. On the trials, there's, I would say as a computer scientist, I personally, and I think the computer science community is just starting to wake up to the subtleties and the scientific challenges here. One thing that happens between medical research and computer science research is there's an overexuberance of optimism that comes in both directions. Computer scientists look at some of the problems in medical research and think, there's a lot of common sense that could be applied based on our computer science knowledge, and we should be able to tackle these things. And then medical researchers, I found, sometimes look at computer science and are dazzled by all of this AI advancement. And, it's dangerous because it's sort of half true in both directions, but it leads to sometimes an over-optimism that can lead to some mistakes and some things that sometimes aren't safe. And so when we're talking about trials specifically, we're now, at least classically, not in the realm of retrospective correlation. So what I mean by that is when we're doing machine learning classically, we're taking data retrospectively, retrospective observations, and then finding correlations, and then codifying those into a model. Medical advancements are based on prospective causation, meaning you set up a trial with specific endpoints, and then you work forwards from there and not look for correlations statistically in the patterns, but you look for causation, that A causes B. And so those are two very distinctive things. They're related for sure. And retrospective correlation is going to be useful for prospective causality, but they're not exactly the same. And so, working these things, reconciling these things is something that's going to be important. I have Eric Topol's book, Deep Medicine, back there, and Eric has written extensively about this distinction. Maybe he's written more words on this subject than anyone else, at least in the medical science community. But I if there's one thing that may be important that has come out of the emergency response to COVID-19, it's focused a lot of attention on this issue, because we were in a situation where there was a lot of compassionate use of experimental therapies. And now looking at that data from that experience retrospectively. We want to understand prospectively, how to treat people. And that's, I think it's causing us to make a lot of progress very quickly.
Recently, or maybe it's a couple of years ago now, they trained an AI to play Go. And originally they had done chess, and it did pretty good at chess, although it beat a specific person. I'm not sure it was the greatest chess player in the world. It just was trained to beat this one person. But in Go, it actually made moves that nobody's ever made in history. It thought through new paradigms. As you see things like quantum computing coming online, which isn't just faster, it thinks differently. How do you think that's going to affect the world that we live in terms of these technologies?
Yeah, I think when we're talking about these game playing systems, they are different than the other things we've talked about, because I've mentioned digital exhaust from human thought and activity. Well, if you're training an AI system from that, roughly speaking, your AI system is in some fundamental sense limited by human intelligence. So, if you train a chess playing machine just only on the observations of human chess players, you're going to have certain limits. What is interesting about chess playing programs and things like AlphaGo is that since you know the rules of the game and it's so constrained, you can simulate huge numbers of games that humans have never played, and you can start to learn things that humans would never have had time to learn, because we haven't been on the planet long enough and haven't been playing Go long enough. And so based on that, you have the potential to develop an intelligence, at least for playing Go, that's superhuman. And in the real world, so for example, in one effort that involves this idea of reinforcement learning, the very large global shipping company, OOCL, they need to be able to have very precise scheduling of ships and ports for managing the global supply chain. And so what you can do is you can simulate the world and then play it forward for 10 years, 100 years, 1,000 years, and simulate scenarios that have never happened in human history, but could still happen. And from that, train a model then that no amount of past experience would necessarily prepare you for. And so these sorts of systems exhibit a form of superhuman intelligence. And I think that they also are alluring to a tech company like Microsoft, because one of the most expensive and challenging parts of AI is getting a hold of data and getting human labels on that data for training purposes. So if we can free ourselves from that, we not only have this sort of potential for this superhuman effect, but we might also then be relieved of the expense and labor of having to deal with a lot of, and regulatory and privacy issues of having to deal with a lot of data. So that's a dream that is fueling a lot of fundamental research in areas like reinforcement learning. It's still, while there are spectacular examples of the potential like AlphaGo or a few narrowly constrained real world examples like our OOCL global shipping example, general purpose reinforcement learning systems in the real world are still it's still very early days.
Peter, thank you so much. Thank you so much for coming on. There's a lot to think about here.
Yeah. Thank you, Peter. That was fantastic. Really appreciate you spending some time with us today.
Yeah, it was good to chat.
Yeah, it's great. Well, we'll catch up down the road, but thank you for coming for sure.
Great.
This is great.
Thanks.
Wow, he was incredible. Boy, he had a lot to say about a lot of different subjects. Always trying to find a deeper insight into artificial intelligence. What did you think?
Yeah, absolutely. I think what's really important here is that the applications in healthcare are incredible, and what is possible, and to really be thinking about this idea of using AI to really go after the cancer and then hopefully move on, I don't think people have any idea about that. And I think what it encouraged me to think about is, how do we get more people to feel comfortable around like electronic health records and all the things that we're going to need to have that data that can be helpful. And balancing that with the fear, because people are afraid of AI. So, I think he talked a lot about that balance. I think it's really important what they're doing.
Yeah, I agree.
All right.
I'll see you on the next one.
See you later.